tablet. Okay, as we go through community ecology, you're going to hear a lot of familiar terms and everything like that. That's one of the things about ecology. A lot of these themes keep recurring. So even though some of these chapters seem a little lengthy, what you're going to find is that there is some overlap, which might make it a little bit easier for you guys to digest. Yes, I do the exams graded, and I'll pass them back to you in the class. Community, we've had this definition before. Assemblage of populations of different species living close enough together for potential interaction. Tweak the definition a little bit. If I were ever to ask you for definitions, and I might give you something a little bit different for a term because it's in two different locations and it might need a little tweaking to fit better into a location. Whatever you give me, as long as it's correct, I'll be okay with that. All organisms that inhabit a particular area. No, that's not a real picture. It's from a commercial a few years back. Mine would be all over that zebra. But in here, oh, that looks nice. Yeah.
Disney movies aren't documentaries?
Do what?
Disney movies aren't documentaries?
Believe it or not.
Believe it or not.
And they start eating animals. I don't stop animals. Madagascar looks pretty good around here. No, not that Madagascar. That's DreamWorks anyway. Yeah, there's a movie coming out about Madagascar. It's a documentary. It's got to be real. Morgan Freeman narrates it.
If you play God for that long,
you got to be right.
So community. Again, assemblage of populations of different species living close enough together for potential interactions. Whether they do or they don't, they have the opportunity to. All organisms that inhabit a particular area. Interspecific interactions. We've talked in here before about intraspecific interactions. Might even come up again with Darwin's finches, where you have the same species interacting with each other. Interspecific is different species interacting with each other. Now let's go back to interstate highways. Interstates run between all the different states. If it was an intrastate highway system, we would just run within one state. Which begs the question, why does Hawaii have an interstate system? They should have an intrastate system. I have questions. So relationship between two or more species within a community. The red-billed oxpecker and the rhinoceros. You can't see it, this little bird sitting right here on this rhino. What it's doing is going around picking the ticks off the rhino. The rhino is not harmed by it, actually kind of benefits from it. The bird gets food from it, everybody wins. Yes?
What about like those little feeders underneath the sharks?
We'll get to that. Those feeders are called remoras. Yes. We'll get to that. Say that again? I've not heard of that. They might, because the ticks will draw blood, so maybe they feed off that too. There are birds. We talked about Darwin's finches. There's actually a vampire finch that'll feed off the blood of other birds. Crazy. Yeah.
like Twilight.
Yeah.
Do they sparkle in the sun?
There's a whole other species of finches that's like turned canine. It's crazy. So interspecific interactions. Competition. You guys know what competition is, but what does it mean in nature for competition to occur? Contest between same or different species who live in the same environment and strive for a goal or resource that cannot be shared. Usually these resources are very limited. And whether you achieve this goal or not could mean everything between your survival or not. Carries both beneficial and detrimental effects. How can competition be beneficial?
Weeds out the losers.
Okay, that could kind of be, but let's think about the winners. How does that benefit the winners? What does it do for the winners?
It leaves more resources.
More resources.
The mates.
You could win mates, sure.
The winners become more advanced.
That's it. Winners become more advanced, more developed, more evolved. Darwin believed that the competition had a lot to do with everything. We'll touch on that in a second. How is it detrimental? Go ahead with what you said before.
We would
Which one?
just a few minutes ago when I said, how is competition beneficial?
It was at the losers.
Okay, how is that detrimental? Because somebody's got to lose, right? There are going to be losers. Not everybody's going to survive. That's okay. Nature is not this happy-go-lucky thing where everybody wins in the end. It's not like kindergarten, okay? There are going to be some winners and there are going to be some losers, but that's what makes nature better. Okay? This could be the driving force behind evolution, that those who win are more advanced, more evolved, developed better characteristics, and these are the characteristics they pass on to their offspring. And that's natural selection. Weeding out the bad characteristics, passing on the good ones, that's natural selection, and that is the driving force for evolution. In this picture here, we've got a dead zebra. If you look in the background, there's no more zebras around. The herd's gone. This is maybe a straggler, might have been an old one, young one, whatever the case might be, injured. It died, whether it was taken down or whatever. Here's the lion, looks like it's got first dibs. You've got a hyena waiting here. That'll probably be second in line. It'll eat whatever the lion leaves behind. And then the vultures will pick at whatever the hyena leaves behind. So, competition. So Darwin comes up with this competitive exclusion principle. What it says, when two species compete for the same limiting resource, one species will use the resource more efficiently, causing the local elimination of the other. Not saying that if that lion eats that zebra that all hyenas are going to go extinct. But it might adversely affect that hyena family. Maybe the parents might get something and the kids might have to go hungry. Or maybe one of the parents gets something and another member of the population doesn't, as a pack of hyenas. One species can either move out, die out, or adapt. So, you look at it this way. There's too limited resources here, too few resources. If I stick around, there's never going to be enough. I'm moving on. So you go to a different area. Maybe you follow the zebra herd and you stick with them. Because there's always going to be stragglers, there's always going to be old ones dying, there's always going to be ones getting injured. You just sit in one place and wait for the herd to pass through, there may never be enough food. You die out. If you sit in that place and you hope that maybe the herd will come tomorrow, and tomorrow never comes, and neither does the herd, then yeah, resources might be gone and there may never be enough food. Or you adapt. Maybe you give up on eating zebras and you go for something else. Maybe something that's a little more plentiful. Maybe until the herds come back and start hunting rodents or something like that. Whatever it takes to get you through. So, competitive exclusion principle, again, a possible mechanism for natural selection. The competition drives natural selection, which could ultimately drive evolution. So in nature, competition is a good thing. It breeds stronger organisms. Ecological niche. Sum total of species use of biotic and abiotic resources in the habitat. Your niche is your job. It's what you get up and do every day. In nature, everybody has a job. You just don't sit around and let somebody else do the work for you. You do that, you die. A species' role in nature and how it fits into its ecosystem. I like this picture. Hyena looks like it has just won the lottery. He's sitting there with what might have been an antelope of some kind, with the head in his mouth like he's the victor. He's got it. He'll take it home and try and get the brain out. Hyenas are predators, basically. They have a very strong bite, powerful enough to break into bone, to get the marrow out. It's very nutrient rich, something that a lot of organisms may not be able to get to because their teeth aren't adapted to that, or their jaws aren't strong enough to bite into it. That's their role in nature, to come through and clean out what's left of the kills. They also have the ability to take down prey on their own. They're much more effective as scavengers. So his role in nature is scavenger. Ecological middle of the species' use of biotic and abiotic resources in its habitat, how an organism best utilizes all the resources it has. So it's its role in nature, how it fits into the ecosystem, its job, it's what it gets up and does every day or every night. It's nocturnal. Resource partitioning. Situation in which evolution by natural selection results in one species using a different set of resources when faced with competition. Again, back to Darwin's finches. It's a classic example. And if I keep using it over and over, maybe it'll make sense as to why it is such a classic example. I don't think all these finches were on the Galapagos Island. I like the picture when it says the many varieties of finches. It gets a point across, it illustrates. So again, a flock of finches were blown off the coast of South America out to the Galapagos Islands. They were all seed-eating finches. Ate nothing but seeds, particular kinds of seeds, in fact. Got to the point where the seeds were not enough to support the entire flock of finches that were now on the Galapagos Islands. So, got together, they had a meeting, they said, we can't keep doing this. If we all keep eating the same stupid seeds, we're all going to die. We've got to do something else. And so probably the older, the bigger ones, whatever the case might have been, said, hey, we're going to keep eating those seeds. I don't know what you guys are going to do, but we're going to keep eating the seeds. So some of them thought and said, okay, well, we'll eat seeds of another plant. Or we'll eat other parts of other plants. You can try that stuff. Maybe it'll be tastier than seeds, easier on the bills, that's for sure. And some even decided to start eating insects, exploiting an entirely different food source. And so this is the resource partitioning part, where you're not eating the same thing anymore because there's not going to be enough of it. So you start exploiting other resources, trying to find something. And this is what led to adaptive radiation, all the change in the finches over a relatively short period of time. Because you're eating different foods, your beaks are going to adapt to be better suited to obtaining those foods. Some people believe that evolution is driven entirely by diet. That's why we're at the top of the evolutionary ladder, because we'll eat anything. Who knows? Character displacement. Tendency for certain characteristics to be more divergent in overlapping populations of two species than in separate populations of the same two species. And I know it's like, what? Okay, I've got two different finches here. Geospiza fuliginosa and Geospiza fortis. No, I don't expect you to remember that. They have overlapping territories in some areas. Some areas you just have G. fuliginosa, others G. fortis. Some areas they overlap. Tendency for certain characteristics, in this we're going to look at beak depth, or how long the beak is, to be more divergent, to be more different in overlapping populations. We talk about convergent evolution, that's where two traits come together, two species come together. Convergent is when they go in the opposite directions, away from each other. In overlapping populations of two species and in separate populations of the same two species. So if these two species overlap, they're together. We seem to see a bigger difference in the beaks than if they're on two different areas. Character displacement. Tendency for certain characteristics like beak depth to be more divergent, more different when the populations overlap or in the same area than in separate populations of the same two species. Look at it this way. It's going back to the idea of competition. If your beaks are similar in size and you're in the same area, then you're going to be exploiting the same foods, and that's not going to work. So maybe you need to exploit a little bit different food that's going to change the length or the depth of the beak. So when you're in an area with somebody else, it's going to force you to change a little bit more than if you're in an area by yourself. That's why the beaks diverge. So here we have it. G. fuliginosa and G. fortis. The beak depth, which shows G. fortis much deeper beak depth than G. fuliginosa. The colors indicate what's the populations. So here I have one population of G. fuliginosa, one of G. fortis. And you notice they're a little bit closer, a little bit farther apart than the median here. Okay? If I'm right here in the middle, they're both averaging out about the same But when you put the two populations together, you see significant differences. They push away from the middle, and the beak depth gets more significant. So when they're closer together, these two being on the same island, these two being on two entirely different islands, then it causes them to undergo sympatric characteristics, similar characteristics. Predation. Now it gets a little bit easier because this stuff you know. Ecology is not that difficult, but then when you throw in stuff like character displacement, resource partitioning, competitive inclusion principles, it's things that might be a little bit harder for you to wrap your minds around. You're not learning body parts. You're not learning things you've heard of before. Now you might be getting into areas that might be a little bit different. That doesn't mean it's hard. Understand it, work it, know it. Stuff isn't difficult. It's just expanding what we've already learned when we start talking about it. Stuff like this, though, is pretty easy. Predation interaction between two species, and with one species, the predator kills and eats the other species, which is the prey. Take this wildebeest, we'll talk more about later, and this crocodile, which is the predator. The crocodile. You bet all questions aren't that easy, right? The wildebeest are migrating. They can't stay in an area for too long because they exceed the carrying capacity. Talked about that already. They've got to push on, move on, because they'll deplete the resources if they stay in one area for too long. Plus, they tend to follow the rain, too. In Africa, it's all about the water, and they have their rainy season, so you kind of follow the rain. In their migratory path, there is a river they have to cross. And the crocodiles know this, and now they hang out at this river knowing that these wildebeest are going to be arriving, and it's going to be like a buffet. Just one right after the other, trying to make it across right in front of you. Yes?
When we talk about natural selection, like with the finches and stuff, was it the same for when the human race started out and there was maybe two different types of humans? Does that ever happen?
Sure. I mean, not so much two different types of humans, but hominids, yes.
So,
Where you had Homo sapiens, Homo habilis, Homo erectus, which all came before us. We were on Earth at the same time as Neanderthals and Homo floresiensis, so that's three different ones on the same planet at the same time. Yeah, now we're in a really unusual place, but there's only one of us, one species of humans. But at any given time, there's always been at least two, and sometimes three. But yeah, and what happened to the ones before? Did the ones that come later, did they evolve from the ones before? Did they pop up independently and merge together, and they emerged as the more superior race? We don't know. Characteristics of predators. Acute senses, adaptations to catch and subdue prey, pursuit, being fast and agile, ambush, using camouflage, or even sometimes mimicry. Okay, we've got an emerald tree boa. It's a big snake, constrictor. It's not venomous. What it'll do is it'll bite and hold on and wrap its body around its prey. But how does it find that prey? Well, it's got these pits on the side of its head, and these pits detect heat. So if something warm passes by, it knows it's there. Plus, it's got that tongue that always sticks out. That just makes snakes even creepier, right? That forked tongue that comes out. What it's doing is it's tasting its environment. When that tongue comes back in, it brushes against the roof of the mouth where there's an organ called Jacobson's organ there, and it tells the snake what it's tasting. Adaptations to catch and subdue prey. I like that picture of the eagle. It's got its talons out. It's ready to grab a fish out of the water. It's got a very sharp hooked beak to pull the things apart. So very well adapted at catching and subduing prey. Fast and agile, you got to talk about the cheetah. This guy is designed for speed. Small head, very rigid spine, flat, long tail to use as a rudder, enlarged heart, chest for greater cardiovascular work. Its claws, unlike most cats, are always out. Uses them for traction. Ambush, camouflage. I don't know if you noticed it yet, but inside this lily is a praying mantis, which also kind of falls under the category of mimicry, blending in to look like the flower. It'll sit in there waiting for something to come to the flower. Bee, butterfly, moth, hummingbird even. Yes, praying mantises have taken down hummingbirds. And it'll sit there and it'll ambush. It'll attack because it looks like something else. Don't fear. Prey are not entirely helpless. They have their adaptations as well. Hiding, fleeing. We've already talked about the snowshoe hare. I like this picture because look at the size of those hind feet. Oh my goodness. I guess I'm wearing the shoe boxes, not the shoes. And he blends in. His color changes to blend into the environment. Mechanical, chemical defenses. You've got the porcupine and the skunk. Porcupine with the mechanical. It's got those spines that it can cause to go erect, making it very hard to want to pet. No, it doesn't grow the spines. Sometimes, like your hairs, they become loose. And so when it makes them erect, these spines come off the skin. The skunk has a chemical defense. But like anything in nature, it takes a lot of energy to make up that chemical, and once it's spent, it's gone. And so what it'll do is it'll warn you before it sprays. And it does this cute little thing where it'll pat its tiny little feet and charge you. Do it a second time and charge you. And if you're still stupid enough to hang around and see what it does next, do it a third time, and it forms its body into the shape of a U because it wants to see where it's going to be targeting. Lands under its tail, lifts its tail, and shoots. Soap and water doesn't take the stuff off people. Maybe it's supposed to be pretty good at it. Alarm calls, distractions. We've got meerkats. Anytime you look at meerkats, there's usually always one looking. Usually looking up because that's where most of the predators come from, the sky, in the form of something like a hawk or an eagle or some kind of bird of prey. Once they see one, they make a noise, everybody scrambles underground. I like this one. This is the car that you find in Central and South America. It's a mockingbird. Okay, this could easily eat this, but mockingbirds aren't programmed to be afraid of things like that. They're programmed to be annoying and defensive. So what's happened is this car has wandered too close to the mockingbird's territory. And what it's going to do is try and lead it out of its territory and then chase it out of its territory to protect its young birds. And so it'll fly and annoy this thing to the point where it'll eventually take off. Check it out around here. I have seen mockingbirds take off after ravens that are like 10 times bigger than them. After hawks that could easily turn around and beat them, they have no fear. The mockingbirds back east are a little more aggressive than the ones out here because they'll actually go after people. The state bird in Tennessee is the mockingbird. And so, being at the University of Tennessee, it was always fun in the spring of the year to find a place where there was a mockingbird nest, especially if it was close to a walkway. People go back and forth on the walkway. The mockingbird doesn't know they don't care about the bird. It's just protecting its territory. So I'd always take my lunch, sit out in a place like this, and just watch the mockingbird just dive bomb somebody and hit him in the head. It was hilarious. And then it was always fun to watch what happened next. Because people kind of look around like, did anybody else see that happen? Was it just me? And so they'll step off to the side somewhere, and you just see this happen over and over again. And they'll sit there and they'll watch to see somebody else get nailed. And they feel pretty good about themselves and they go on. And you can just see this pattern repeated over and over again. It's just human nature. Cryptid coloration camouflage. These are the English pepper moths, and there are two of them here. You see the light colored one here. I don't know if you've seen the darker colored one yet. Classic case of cryptid coloration versus ecology. The light colored one is the normal native color. It stands out on the dark bark, but on the light colored bark it blends in. Most of the trees in England at the time, English pepper moths, were light colored, so it blended in very nicely. But then what happened is pollution, industrial revolution, on up until about the 50s or 60s when the environmental movement started. The trees went dark, and so if there was a bird coming along on the light colored bark, it would go after the dark moths. Now on the dark moth, the bark, the light colored moths. So it would actually dictate which moths would survive by their coloration to how well they blended into their environment. Now with the environmental movement, the trees are lighter in color again, so you have more of these moths because these guys stand out and get eaten. Yes?
Can skunk, did you say it can only spray once?
Well, not in its entire life, but once, and once it depletes it, it has to build up its stores again.
Oh, I see, okay.
Yeah, no, it can multiple times.
Oh.
Probably takes a couple hours, a day or so.
Oh, okay.
Professor Ralston?
Yeah.
Why does the mockingbird have no fear?
It's just the way it's programmed.
It's just
territoriality.
okay.
Being territorial pretty much overrides everything else. Just what it does.
Okay.
Other characteristics of prey, aposematic coloration. Simply a bright color warning exhibited by potentially dangerous species. Example, poison arrow frogs. All very brightly colored. Funny thing is, in captivity, they tend to lose their toxicity. Chances are it's something they get from the environment, something they eat that causes them to be toxic. They're called the poison arrow or sometimes poison dart frogs because what natives will do is they'll get like a bag of these frogs, hold them over a fire, warm them up just a little bit, not cooking them, just warm them up a little bit, stresses them out, and they secrete this toxin in their skin. And they'll put their arrows in, and they'll go hunting because whatever they touch with those arrows, it's going to die. That's how lethal this stuff is. Like I said, in captivity, they don't seem to be quite so lethal. Yes? I'm not sure exactly what their diet is, but it's something in nature that I'm sure. Yeah.
Do they lose their color too?
No, they'll keep the color. Yeah, that just kind of goes with the territory. So cosmetic coloration. Batesian mimicry. We don't like snakes, they bad to be here. Bates and Mueller were two early naturalists, and that's where the names come from. Batesian mimicry, when one species copies another species, which tends to be harmful. Coral snake left, the scarlet king snake in the middle, and the scarlet milk snake on the right. This is the toxic one, the harmful one, poisonous one. Red on black, friend of Jack. Black on yellow, Jack's a dead fellow. So if the red and the black don't touch the snake, okay? This is venomous, but in nature, a way of kind of like helping the species out, these develop a similar color pattern. Of course, you probably don't want to hang around long enough to think of that little rhyme and think, well, wait a second, is it venomous or not? In movies, you always see these two. You hardly ever see this one. Go figure.
Where'd you learn that rhyme?
That's just a common rhyme.
Really?
So the red and the black, if they're not touching them,
Red on black, friend of Jack. Red on yellow, Jack's a dead fellow. Red on yellow, Jack's a dead fellow. I can't keep this straight. There's not around here, so don't worry about it. Coral's not going to take us out.
Yeah.
So you're okay.
Like the other version that line is red touch yellow, yellow fellow, red touch black, black staff.
Yeah, there's a couple different variations to it. Muellerian mimicry, when one species copies another species, which tends to be distasteful. The viceroy butterfly and the monarch. You look at these, and if you look close, you'll see differences. Most birds aren't going to look close enough. The monarch is a terrible tasting butterfly. Not that I've tasted one before. Just know it. I don't need to taste it. I know it. So what the viceroy does is kind of borrow the coloration and the pattern of this guy, because let's say a bird eats one of these, makes the bird sick, it never wants to eat one of these again. Well, odds are, if it sees this, it'll never want to eat one of these again. So basically what you're doing is you're doubling your chances for survival if you mimic a species that tends to be distasteful, just like the snakes. If you look similar to something else, it tends to be dangerous or distasteful, and chances are you're going to be left alone. Just on the safe side. If you look up here, you get a little more orange up here, not up here. You look at the pattern along the edges, it changes as well. But yeah, it's really hard to tell. That's what taxonomists do. They look at this and they look at the minutiae, the very insignificant details, and how to distinguish one species from another. So if you're OCD, taxonomist.
Professor Rossi?
Yes.
So this one just has to be with like bugs that are just pretty much distasteful?
As long as they're similar to each other, yeah.
Okay, it's not like the butterfly would dress up like another butterfly to kind of scare something
No,
away.
not in that case. There are situations like that if you mimic a harmful species. There's the can't think of the name of the butterfly now. But yeah, it looks like a snake is a caterpillar.
Okay.
And it's not going to try, it's just self-preservation in that case.
All right.
It's going to mimic something like that, but it's not so, something that will leave, well, it will be. So if a bird comes to see it, it'll leave it alone thinking it's a small snake. Now, it's not going to fool the bird for long, but it might be enough that it allows the caterpillar to escape.
Okay.
Herbivory. Even plants have a strategy for protection. A form of predation in which an organism principally consumes autotrophs such as plants, algae, and photosynthesizing bacteria. Some plants have chemical weapons. Nicotine and peppermint are chemical weapons. Now, nicotine you probably get because we know how bad that is for smoking. Cincinnati Zoo, they've got one of the nicest insect houses I've ever seen at a zoo. And even before it became fashionable to knock the smoke inside, they had signs all over the building saying no smoking, that nicotine is an insecticide. And you just see some guy with a big cigar walking through there, just all the exhibits dying as he passes by. Peppermint. You might be thinking, wait a second, I like peppermint. I like it in my candy, I like it in my tea. How can you say that's a chemical weapon? Well, you're eating refined peppermint, not the full-blown, natural, strong peppermint that is really too strong to be eaten. Chemical weapons, spines, thorns. That's the acacia tree. That big thing that you see coming in with its tongue sticking out, that's a giraffe. Giraffes can work around the spines and the thorns. Not many other things can. Usually it discourages most things, but the giraffe and the acacia have a long history together, and they're okay with that. So like I said, even plants have a defensive strategy. Parasitism. Interaction between two species in which one species, the parasite, usually smaller, derives nourishment from the other species, while the other species, the host, is harmed. The host is usually larger. Think about it this way. If ticks were the size of golden retrievers, you'd have one on you and you'd be sucked dry. It wouldn't do the tick any good, and it certainly wouldn't do you any good. The job of the parasite is to feed off a host, not to kill the host. Parasites are killing hosts only because they haven't evolved together long enough to figure each other out. Because when the host dies, the parasite dies. At least extra plenty of the food source. So, one benefits, one is harmed. That's parasitism. Now we're going to be talking about several different relationships where, in this case, one benefits, one's harmed. We'll talk about some where they both benefit, some where one benefits, the other one's neither harmed nor helped. There's a lot of different kinds of relationships within a community. Headlights. Crazy. Look at the legs of these things. Very specifically designed for hair. And that will even distinguish between regular hair and, well, pubic hair. And it's all because of the attachments that allow them to cling onto the hair. One of my favorite poems in English literature, what can I say? This is all that's coming out of me, was Ode to a Louse. And you may not have heard of the poem, but I know you've heard of the poet, Robert Burns. He's the one that wrote Auld Lang Syne, and we sing every year at New Year's Eve. He's sitting in church on Sunday morning, he sees this woman coming in down front. She is just the most elegantly dressed woman he's ever seen. But I guess the sermon wasn't too interesting because he's just sitting there watching her. And as he's watching her, he sees this louse crawl out from her hair onto the brim of her hat. And that inspired his poem. He was an alcoholic too, maybe that hits him. Anyway, one of the best lines in there is, all the power that gift he sees us, if we can see ourselves as others see us. Because, you might fix yourself up and you think whatever you're wearing looks great. Well, hair is perfect, makeup's just right, whatever. And you go out and people might look at you and think, oh my goodness, is your house not 10 years? Flip it this way, you go to the home, people running around, or you go to because they don't see you as you see. I see people that are just say different than me, and I'm thinking, thank goodness, because if everybody was like me, this would be a pretty boring place. But I like that line. All the power that gives us, if we could see ourselves, others see us. Many parasites have complex life cycles. Some can even alter behavior of host, increase the probability of being transferred to the next host. I'm going to show you the life cycle of toxoplasmosis in a second. This was something else I studied in research. Toxoplasmosis is a protist. Toxoplasmosis gondii. Toxoplasma gondii. I did that wrong. I studied it. I should have known better. Anyway, it's a parasite. It's a protist. And what it does is it wants to get into cats because cats are the primary host. And this is why when women get pregnant, they say, if you got a cat, don't change the litter box. Let somebody else do that for you. Because it could be transferred from the host, the cat, through the feces, to the woman, into the fetus. Now, normally, toxoplasmosis isn't dangerous to people. It will get inside of you and it will go dormant because your immune system keeps it in check. But if you're a newborn, a little baby, preborn, your immune system isn't quite intact yet, and it could have severe side effects to a fetus developing. If you have it inside of you and your immune system gets suppressed, HIV, for instance, can suppress your immune system. What can happen is it can reappear, and it has detrimental effects too. The reason I studied this, most of the time we're studying herpes viruses, not protists, but their life cycles, their natural histories are very similar to each other. They get into the nervous system, they'll lay dormant there, unless the immune system becomes suppressed, and then what happens is they attack the nervous system. So, mice are like a secondary host. And what toxoplasmosis does is somehow the mouse overcomes its fear of cats and will have no problem hanging out with cats. Some people theorize it's just something in the brain, a behavioral abnormality that occurs. Some people say it's the odor of the cat urine that the mice are attracted to for some reason. Anyway, it puts it in the city of the cat eats the mouse. So here we have the definitive host, the primary host of toxoplasmosis. It gets it from predation through mice. You get it from feces through cows. Regardless, it ends up in women, and what happens is congenital transmission that while she's pregnant, it could be transferred from the cat through the feces into the woman, and then into the baby. Organ transplant or blood transfusion is how we get from person to person. So, pretty scary disease. As long as your immune system's in check or you're not pregnant, it's not bad. Mutualism. Interaction between two species in which both benefit. We talk about symbiosis a lot. And the problem with symbiosis is that a lot of people misunderstand. Symbiosis is two organisms living together, period. A lot of times they associate mutualism with symbiosis, where two organisms live together and both benefit. One example, acacia trees often have ants living on them, which feed on nectaries produced by the trees. Produced by the trees. This is a nectary. The ants feeding on it. It's like sugar water. The trees produce this to attract the ants, to keep the ants. Ants will attack other animals that feed on the tree. If other insects invade their tree, they'll take them out. And we'll even cut off small branches of other trees that come in contact with their tree. There's another tree growing close to the acacia tree that might interfere with their tree's growth. They'll climb up into the other tree and prune it. Mutualism. Usually a situation like this requires a lot of co-evolution. Lots and lots of co-evolution. Two organisms growing together, figuring each other out. Like a very, very long and trying marriage. Once you get through the trials, once you figure each other out, they live happily ever after. Coevolution usually occurs between mutualistic species. Methanogens and herbivores. We have those living in us because we eat plant material. And what it does is help us to break down some hard to digest plant material. Maybe not completely, but to some degree. Nitrogen-fixing bacteria and legumes. We'll talk more about these. And these little nodules in here, you will have, in plant roots, you will have nitrogen-fixing bacteria that takes the nitrogen from the atmosphere, which the plants can't directly use and convert it to the form they can use. Mycorrhizae in plant roots. You can see the yellower plant roots coming down, a few strands here, and all these extensions coming off. These are the and mycorrhizas. We talked about those when we talked about fungi. And then lichens, and I hope you remembered lichens. I'm probably never going to ask you about it again. But remember that lichens are a combination of what?
Algae and
We might
fungi.
have
Algae and fungi.
algae, right. What does fungus do?
Provides that
Shelter, place to live, habitat. What does the algae do?
Food.
Nutrients, nutrition. Very good. Hope you guys should. So, coevolution. These things evolve together to figure each other out. They find benefits in their cohabitation, and it leads to two stronger species.
So the lichens is a mutualistic relationship. It's not symbiotic. It's not
Well,
symbiotic.
It is symbiotic because symbiotic is the two organisms living together. And like I said, that gets confused a lot because a lot of people make symbiosis and mutualism synonymous, and they're really not. Mutualism is a type of symbiosis. Okay, let's take a break here. Ramon, when we come back, there's your shark with the Morris. Are you the biology club? Yes. Yeah, it's biology club.
Okay, hi, I'm Michelle. This is Jose. Our last bio club meeting of the semester is today at 12 in MSTC 202. And if you guys bought any shirts, I'll be giving them out.
Next exercise is going to be the last meeting. It's going to be about mostly officers for next semester, so we can keep the book going. So, show up.
Yay.
Okay, commensalism. Interaction between two species, which one species benefits, the other is neither harmed nor benefited. Doesn't matter if they're there or not. Doesn't care. It's more of an indirect relationship. For instance, sharks and remoras. These things underneath the remoras, we used to have them at the Cincinnati Zoo. It was funny. People would walk in and see them swimming around with the sharks and everything. Aw, it's got babies. No, it's the babies. What the remoras do is they hang out near the sharks because then those sharks can't really eat very neatly. The shark will take a big chunk of something, shake its head back a couple of times, and break off a smaller bite. Well, in all this fury of trying to get a bite-sized piece of whatever, killer whale, dolphin, surfer, what it does is it distributes food all around, and these guys will be there to pick up the little pieces the shark don't eat. Herbivores and cattle egrets. We mentioned the cattle egret before, how it's kind of spread all the way from its original area. What they do is they just kind of hang out. Because as this big herbivore is going through eating the grasses, he's displacing a lot of insects. And the cattle egret's sitting there waiting for the insects to be displaced, and it gobbles them up. It doesn't matter what this guy does as long as he's eating, and this guy's just going to hang out. Well, when you get some insects kicking up and moving around, I'll be there to catch it. Yes?
Do the sharks ever eat those?
Not that I know of.
That's what I was thinking.
I think we'll get into that later. Why they wouldn't eat the remoras. Okay, trophic structure. Shifting gears a little bit. Food chain, transfer of energy through logic trophic levels. We've got the grasses or some type of plant, the producers. We've got the hare that'll feed on the plants. They're the primary consumers. We've got the coyotes that'll feed on the hares. They're secondary consumers. Transfer of energy. The sunlight is the beginning of all energy for all ecosystems. The plants are really good at absorbing that sunlight and turning it into food. The rabbits eat that food. Energy is transferred from the sun to the plants to the rabbits. And then what happens is the coyote feeds on the rabbits, so the energy is now transferred from the sunlight to the plants, to the rabbits to the coyote. Now it's got to be logical. This works. You can't say something like, okay, how about algae, penguins, and polar bears? Well, there's a lot of things wrong with that. First of all, penguins don't feed on algae, they're fish eaters. And another thing is, polar bears and penguins live on opposite sides of the world. Please don't get your biology by Coca-Cola commercials. They're wrong. I've had friends tell me, I don't know what the deal is with all the polar bears and this global warming. They got all those penguins to eat. So it's got to be logical. It's got to make sense. A food web. Food chain. A lot of food chains together, you get a food web. Elaborate interconnected food chains to create more stability in an ecosystem. What that means is, if you eat one thing and one thing only, you're pretty limited. But if something happens to that one thing, it collapses, it dies out, it's a viral infection, it gets gone, then you're stuck. You got nothing. But if you eat more than one thing, then you have more options, more opportunities. So for instance, I've got all these plants, and it's actually a desert food web. I've got rodents and insects that'll feed on the plants. But you see, the arrows go to what eats them. So most of these things are eaten by more than one thing. Or these things eat more than one thing. And then you follow the arrows up. The rodents can be eaten by the snakes, by the hawks, in some cases by the lizards, which will also eat insects. Birds feeding on other parts of the plants. I've got owls that'll feed on insects sometimes, as well as rodents. So in a food web, you're eating more than one thing. It's like you've got a favorite restaurant. You eat just at this restaurant. One day you go and the restaurant's closed. What are you going to do next? Oh my goodness, I don't know. I never ate anywhere else. So food web just gives you more options, creates more stability. If you look at something like koalas or pandas that have a very limited food source. If that food source collapses, then we can start to see a decline in those animals. For the koalas, eucalyptus. For the pandas, it's bamboo. And the bamboo is cyclic. Some years there's more of it than other years. So on those down years, they really have to watch the pandas, make sure they get enough to eat. Okay, breaking the food chain down. First, the producers. Organisms use sunlight for photosynthesis, producing organic molecules from inorganic molecules. Ooh, you're thinking, that sounds so familiar. Where have I heard that before? What's another name for producers? Autotrophs. See, this is the nice side of ecology. I like to call it science light. They're no longer autotrophs. Now we call them producers. Includes green plants and algae. I mean, technically it includes photosynthetic bacteria, but there's not a lot of food chains starting at bacteria. I want to throw them in, that's perfectly all right. So, producers. In case you didn't find it, I did load up the outline for this chapter. So it's there now. So, who else is here? Well, we've got consumers. Organisms that obtain energy as organic molecules from other organisms. They can't make their own food. What do we call these guys before? Not autotrophs, they were heterotrophs. Now they're consumers. And we distinguish one from the other by saying, well, it's either a primary or secondary consumer. These are herbivores, or carnivores, plant eaters, and plant eater eaters. Meat eaters. Food chains just don't have to have 3 steps to them. I just did this because it's easy, it's basic, it's there for you to understand. I could do something like grasses, the rabbit, I could throw in the snake, a hawk that eats the snake, a coyote that eats the hawk, a mountain lion that eats the coyote, a bear that eats the mountain lion, a human that eats the bear. You can keep going as long as you want. But we're going to talk in a few minutes that isn't always ideal. The farther you string a food chain out, the more instability occurs. So consumers, organisms that obtain energy as organic molecules from other organisms. Animals, things that feed on the producers, basically, or the things that eat the producers. The energetic hypothesis. the states, the length of the food chain is limited by inefficiency of energy transfer along the chain. This is going to be a recurring theme. You have 90% energy loss occurring between trophic levels when moving through a food chain. Let me go back a second. The plants can't handle all the energy the sunlight gives to them. It converts some of it into food. From this to the rabbit, only 10% of the energy from the plants is transferred to the rabbit, 90% is lost. From the rabbit to the coyote, only 10% is transferred, 90% is lost. That's what we're saying. And the longer the food chain, the more energy loss there is. So at the very end of the food chain, you have very little energy from what you started with. That's why a long food chain becomes unstable. The shorter the food chain, the more energy transfer you have. That makes sense? There's going to be several hypotheses. Make sure you can tell the difference between them. Energetic hypothesis. Again, length of food chain is limited by inefficiency of energy transfer, having everything to do with the fact that only 10% energy moves from one step in the food chain to the next, where you have a 90% loss from one step. I would want to say it's the same. So a pyramid, only 10% of the energy, followed by the numbers or biomass, is transferred from one trophic level to the next. So it's not just energy, it's also numbers and biomass. We'll talk about numbers and biomass in a second. When we look at the pyramid, it's not like one of those nutritional pyramids that you would learn about in health in grade school. You have so many fruits and vegetables every day, so much protein, so many grains, all that stuff. It's a different type of pyramid. At the base of the pyramid, you always have producers. They're the ones who take the energy from the sunlight and convert it into food. The second level of primary consumables, plant use. Those things that are going to be on the plant, the producers. Third level, you have these secondary consumers. Those that are going to be on the primary consumers. So again, only 10% of energy, numbers, or biomass is transferred from one trophic level. Here's what it looks like. It's got nothing written on it. Just the plants you see make up a huge part of this pyramid. This little yellow section here are the herbivores. Right here are the first carnivores, and up here the second carnivores. And so the pyramid of numbers, biomass, and energy are all below. And you see they all look identical. Start with energy. Again, you have so much energy. Most of it's tied up in the producers. 90% is lost from one level to the next. The other 90% lost from one level to the next. Well, with the energy, you're only going to support X number of organisms. So let's say with all this energy, I can support 1,000 grasses. Well, let's say if I lose 90%, then I can only support 100 rabbits. And let's say if I lose 90%, then I can only support 110 first carnivores. Does that make sense? So if I lose 90% energy, I lose 90% numbers, or I can only maintain 10% of the numbers from one trophic level to the next. Well, biomass is just the dry weight of any organism. So if I take all the grasses and dehydrate them and weigh them, that's my biomass for the dry grasses. Well, grasses are already pretty dry, but you take a bunny and dehydrate that. And yeah, I said bunny because it sounds so much worse, dehydrating a bunny. Sounds like something evil scientists would do. And then weigh that, that's what you get here. And then if you take a fox, dehydrate that, and weigh that, that's what you get there. Think about it, we're like 90% water. So you dehydrate us and then weigh us, there's not much left. And then the biomass of each organism, if the organisms are reduced by 90% from one trophic level to the next, then it only makes sense that the biomass is reduced by 90% from one trophic level to the next. So it's all proportional. Okay, it's all direct proportionality from the energy to the numbers to the biomass. The dynamic stability hypothesis. Long food chains are less stable than short food chains. Yeah. Long food chains are less stable than short food chains. So it's similar to the energetic hypothesis. Kind of go hand in hand. Population fluctuations at lower levels are magnified at higher levels. If unable to recover quickly enough, then extinction of top predators is inevitable. Okay, I've got phytoplankton, which is plants, zooplankton, tiny little animals, small fish feeding on the zooplankton, bigger fish feeding on the small fish feeding on the zooplankton, and then I've got a killer whale feeding on the bigger fish. Let's say something happens to wipe out these fish right here. Let's say a red tide or something like that, some kind of natural disaster. These guys are gone. Well, if these go, then these are going to get gone, and these are going to get gone. So population fluctuations at lower levels are magnified at higher levels. Or let's say even I don't lose all of them, but I lose 50% of them. Because I have fewer carnivores relying on more smaller animals, if I have a reduction here, it's going to significantly reduce the numbers up on top. If I cut this down by 50% and this down by 50%, I see a greater difference because if I go back to this, at the top of the food chain, I have fewer organisms. So a 50% reduction here is going to be significantly greater than a 50% reduction there. So they're magnified at higher levels. If I'm able to recover quickly enough, if I can't get these fish up to their former numbers, then the food chain won't recover. But usually with smaller animals, with lower life forms, they tend to reproduce very quickly in larger numbers. So the dynamic stability hypothesis. Like I said, you're getting several hypotheses today. Make sure you know them and distinguish between them. Next up, the megafauna hypothesis. The big animal hypothesis of literally what megafauna are. The size of the carnivore places an upper limit on the size of the food it can eat. Large carnivores cannot live on small prey due to their inability to acquire enough prey fast enough to meet their metabolic needs. In other words, a lion going after a rat is going to spend way more energy than it's going to get from eating that rat. It's just not worth it. The shark turning, bless you, and trying to feed on the remora. It's going to expend way too much energy. Sharks are fast. They're not that maneuverable. They're quick, but they're not agile. And so it's going to be difficult for him to try and turn and eat that fish. And so he's going to spend a lot more energy than he'll get from those nutrients. It's easier going after something bigger, just taking a big bite out of it, much less energy involved. Same thing with the lion. It's better, especially since lions hunt cooperatively, to take down a bigger prey. So you divide the energy spent among 4 or 5 lions to take down one wildebeest. And then everybody benefits from that. One lion, one rat, a small rat at that, you're not going to get enough energy. So that's the megafauna hypothesis. The size of the food has to suit the size of the predator. Yes?
What about chicken nuggets?
Chicken nuggets, what do you mean?
Don't they go against the megafauna hypothesis?
For us, everything goes against us. We are so unnatural, it's not even funny. I guess you don't know what's like these.
Now I want some chicken nuggets.
You get like
At 3 in the morning,
no,
I
that's
would almost chicken nuggets.
and the dipping sauce do that before.
Oh, yeah.
And now I want some chicken nuggets too.
So now everybody's hungry and everybody's
I know.
checked out, on to lunch mentally at least. So the megafauna hypothesis. Size of the carnivore places an upper limit on the size of food. think about it. If you were hunting, you had a bow and arrow or a gun, would you rather take down something larger or try and take down something smaller than this? You're going to waste a lot more time taking down things like this. Okay, species with significant impact. I think the book, the title is Species with a Large Impact. I don't like large. It's too general. I like the word significant. Okay, species richness and species abundance. I think we've talked about this before. If not, here we go. Total number of different species within a community, species richness. How many different kinds of animals do you have living in a given area? Again, the more different kinds you have, the greater the species diversity. Just like the greater the genetic diversity, the greater the chances for that ecosystem survival. We talked all semester long about how if an organism is more genetically diverse, it has more tools to deal with an environment, more capable of surviving. Same thing's true for the environment. If you have more different kinds of species in an area, the greater the environment's chances are for survival. If anything would happen to any one of those species, it's always got a plan B, something to fall back on. Species abundance, proportion each species represents the total individuals in the community. How many numbers of each kind of species do you have? If you have large numbers, is that a good thing? In a situation like this, yes, having a large number of zebras is a good thing. You don't want a large number of lions with a large number of zebras because there wouldn't be enough food to go around. There's that 90% again. You have to have 10 times more zebras than you do lions, 10 times more prey than you do predators in order to support the predators. Because you're going to lose 90% energy going from the prey to the predator. I got hit like half a dozen different ideas that we talked about today. So species richness and species abundance. That picture I like because it's kind of weird. You're thinking, what's so easy? Anyway, shut up. If you look at it, it looks like a lion's looking at a picture of a herd of zebras. And we're looking at the picture of the lion looking at the picture of the herd of zebras.
Yeah. The camera crew and everything.
Dominant species. Species in a community that are the most abundant or have the highest biomass. I think wildebeest definitely cover that. I threw a picture of wildebeest by itself in case you weren't sure what it looked like. Sometimes they're called news. And you're thinking, what's new? What's new? Yes, I can't believe I did that either. Affects occurrence distribution of other species. If you have a massive herd of wildebeest coming through an area, everything else is going to get out of the way. They're going to redistribute themselves. But you're going to have lions and other predators, leopards, cheetah, hyenas following the herd. They're going to move towards the herd, whereas other things might move away from the herd. So something this big is definitely going to impact where and when other species occur. So dominant species. Now we're going to be talking about different kinds of species. These make up really good multiple choice questions. I'll tell you that right now. Keystone species. Species in a community that serve an important role in their ecological niches. In their role, they have an important job they have to tend to. Nobody else in the community really does. It's like their specialty. They're usually not as abundant as dominant species. If they're good enough at their job, you don't need as many of them. Example, sea otter, sea urchin, and kelp. Not three different keystone species, but what happens here, we're going to talk about how the sea otter is a keystone species and how it impacts sea urchins and kelp. So the three go together in describing the sea otter's role as a keystone species. Species in a community that serve an important role in their ecological niches. Okay, dominant species, they're just there. A sheer number, they are there. And they could or couldn't impact their environment. The keystone species definitely impacts its environment. It's more of a specialist. Food chain for killer whale involvement in the food chain. So we're doing it without. You have kelp, you have sea urchins, you have sea otters. Total kelp density. Before killer whales, kelp density was pretty high. Sea urchin density was pretty low. What happens is sea urchins will feed on kelp, especially new growing baby kelp. What happened was the sea otter abundance started to decline because the killer whales moved in and started feeding on the sea otters. And so their numbers dropped. What that meant was there weren't as many sea otters eating sea urchins, so the sea urchin numbers increased. And what that meant was they started feeding on more kelp, the amount of kelp crashed. Because the sea otter was the keystone species. You eliminate him from the situation, you change the entire environment. Kelp is good, sea urchins not so good. Okay? So when the sea otters disappeared because of the killer whales feeding on them, it allowed the sea urchins to emerge and wipe out the kelp. Foundation species. Species in a community that exert their influence not by numbers of niches, but by behavior that cause physical changes. Beavers and a beaver dam. I mean, it's a rodent, okay? Pretty big rodent, one of the biggest ones in North America, I believe. We don't have a capybara here. Now that would be a rodent I'd be okay with. They have like something, a rodent that weighs like 150 pounds. That'd be kind of cool. You could take that thing for walks on a leash. Okay, here's the dam that this beaver built. Look at how high the water is behind and how low the water is below. That's a significant structure there. It has literally dammed up the water behind it. And so it has altered this. It has flooded this area up here. It's dried out this area down here a little bit. It's going to alter the wildlife you find in here, the plants, the animals. Okay? They're actually trying to reintroduce beavers back into the West. They were hunted because people used to wear their pelts. So they were making hats out of them or like collars for coats or whatever, and the numbers declined. It's for this reason they want to reintroduce the beavers, because they provide wetlands, watering holes for things like cattle. And of course, if this comes back, you're going to get other animals back in that area as well. They're actively trying to reintroduce beavers to some parts of the West. Yes?
What is their reason for doing, like, what do they benefit? Is that just their home? Or?
It's their home, yeah. They'll live inside here. And this is their access in and out. Now, is there feeding purposes too? Maybe. I don't think so, though, really. I think it's just, this is how they build, this is how they live. It's a nice, secure place. I mean, for a predator to get to a beaver, it has to go into the water. A facilitator species, snakes and bats. Man, we're getting all the creepy crawly stuff today. Species in a community that has a positive effect on the survival and reproduction of other species in the community. Fruit bats. Fruit bats eat fruit. Fruit passes through the bats in the form of seeds, and the seeds are deposited. There are some jungles on islands in Asia and in the South Pacific that are totally populated because of fruit bats. That as they flew over, they deposited their seeds from the food they'd eaten, already in fertilizer, already good to go, and these forests grew up. So, hugely responsible, hugely beneficial to communities because they start the communities, they get them to grow. They have formed literally forests of communities. Yes?
What eats bats?
All kinds of stuff will eat bats. It depends on where you are. There are some snakes that are finely tuned enough that they can pick off a bat as it comes out of the caves. Sometimes they'll slither along the bottom of the caves as the bats fall. As far as fruit bats go, they mostly nest in trees, so the same thing would be true for that. Any kind of predator that can catch a bat when it's not in flight. I don't know if there's a lot of flying things like hawks that take out a bat, but yeah, there's definitely enough things moving around. Reptiles, small mammals, things like that. Invasive species. Species in a community that was introduced and has a negative effect on the survival and reproduction of other species in the community. Kind of the opposite of facilitator species. These are the good guys, and these are the bad. Most of the time they don't mean to be bad. Not that I'm saying go out and hug a toad. What I'm saying is, it's because of us. Because of us moving these species somewhere where they don't belong. For instance, the cane toad was introduced to Australia. Australia is one jacked up country when it comes to invasive species. I like Australia. I hope I get there someday. I'd love to check out the country. But they have made mistakes after mistakes. We'll talk more about these in the next chapter or two. 3,000 cane toads were released in Australia in 1935 to battle the cane beetle. On paper, it sounds great. We've got an insect problem. Let's get an insect eater in here. Cane toads never evolved in Australia. What they didn't realize is the cane beetle actually jumps higher than the cane toad. So you just introduce something to the environment to eat something else that it can't catch. Okay, big problem. You also just introduce something to the environment that has a high reproductive rate. They reproduce frequently and in large numbers. Now they number in the millions. You go to Australia the right time of the year, you can participate in things like cane toad festivals, where they give prizes for whoever catches the most cane toads or who catches the biggest one, because they're trying to get people involved to eradicate, to wipe out this pest. Here's the catch. They secrete poison in their skins. So you don't want to be touching them too much. You definitely don't want to be licking them, although some people do. So it's wiping out wildlife because something will try and eat it, and it will get a mouthful of toxin and it will die. The other thing is, they get pretty big, about the size of a dinner plate.
Wow.
And so they can pretty much eat anything that's smaller than them. So they're wiping out a lot of species that way as well. Huge mistake. Also known as a marine toad, Buphos marinus. So invasive species, never a good idea. Figure out something else in the environment. We're trying to introduce something. We'll talk more about Australia, I think, in 56. A disturbance. This might have gotten thrown in with an abiotic factor. We talked about things like the amount of rainfall, temperature, wind, soil, all this stuff. The amount of sunlight for abiotic factors. Disturbance is another one. Event, natural or man-made, that changes a community, removes organisms, and alters resource availability. You live in Southern California, you know wildfires. Okay, this is a disturbance. You see what's going on here. There's a lot of natural debris, leaf litter and things on the ground. That's what the fire is feeding on. In this country, we only recently figured out that fire is a good thing. That sounds like a caveman. Fire, good. We used to put them out as soon as they started because we didn't want our forests to burn. But who was around 250, 300 years ago when this country really wasn't settled much by Native Americans, and fires would erupt. They would just burn. But that's okay, because some things like a nice fire to burn things out, clean it out, so all this doesn't build up. We kept putting out fires and putting out fires, and then we get all this leaf litter built up, all this natural debris. And so it fuels the fire, making the fires more intense, and even does more destruction than we did with the fire burn. I think Arnold Schwarzenegger, one of his ideas before he left as governor was to make sure that we get all the forests cleaned out, to clean out a lot of this leaf. We've got all these people in prisons. Let them rake leaves or something. I don't know. Do what?
I was like, they do make them pick up trash on the side of the highway.
Sure. It's cleaner than trash. Now, what happens with disturbances? You have two different ways habitats arise. One is through primary succession. It occurs in a virtually lifeless area where no original organisms existed. No soil is present. That last part is pretty significant. That's the big distinguishing factor between primary succession and the next one I'm going to give you, secondary succession. This is White Island off the coast of New Zealand. It's a volcanic island. It's been around for a little while, but not long. You still see a lot of the volcanic rock making up the slopes. You still see the crater there filling in with something that looks like it might be water. Something trailing off here. Look at the edges. You're starting to see green. And this is what happens with primary succession. You've got nothing here. It's just volcanic rock. But then the wind and the salt and the ocean, the water, erodes away at this, creating debris. And maybe you get some lichens blown out here, and they grab onto the side of anything and start to grow. And maybe they trap more debris that you get enough to make soil. And then you can start growing plants because you've got a few seeds that have blown out to the island. So now I've got plants. If I get plants, then birds and insects won't be far behind. And if I get birds and insects, then maybe if I'm lucky, maybe some debris will float out carrying things like reptiles or small mammals to feed on the birds and insects. And now I've got a habitat. But it starts with nothing. No soil is present. That's primary succession. One thing you won't get out there is amphibians. They don't like salt water. Secondary succession occurs when an existing community has been cleared by disturbance, like a wildfire, a hurricane, something that has wiped out the community, but the soil is still present. It didn't take the soil with it. As long as you have soil, you can start over. And that's what we see here. You see the remnants of a forest fire that's burned, and you see some plants already starting to sprout up. That's secondary succession. I think I mentioned before when Mount St. Helens blew in the 1980s, they said it would be decades, bless you, before anything would grow back, and within a decade, life started to come back. That's an example of secondary succession. So again, the important thing to remember, no soil in primary, soil in secondary. Biogeographic factors. To rest a second. Touched on this before. Two major biogeographic factors correlated with species diversity. Altitude and latitude of community. We talked about this before. How high up or how far north or south of the equator. Again, if you go right around the equator, you find most of the tropical rainforest. A little bit above, a little bit below. That's where we find deserts, certain things. Well above the equator, temperate and northern temperate forests. Also, total area it occupies. You're going to find a lot more species diversity in larger land masses than you will in a smaller land mass. It stands to reason. Equatorial versus polar gradients. Life at the equator versus life at the North or South Pole. First of all, the equatorial or tropical communities. When we talk equatorial, we're talking right around the equator. Tends to have a longer growing season. Some things can grow almost year-round, kind of like us. I talk to my family and friends back east. A lot of them are gardeners. I have desert plants that I've planted. I'm not the type that every evening I go home, I get my little gardening outfit, my little gardening tools, and I sit out in the yard and do gardening. I like stuff around the house more than just grass, and I put a lot of desert plants in there so I don't have to deal with them. So last spring, they're happy. I don't have to dig things up every fall and replant them in the spring because our growing season is almost year-round. Back east, the winters are too harsh. Nothing would ever survive. It's a longer growing season. Speciation accelerates 5 times faster. You get more new species, which is what speciation is, faster at the equator than you do at the poles. A lot of it has to do with the longer growing season. If you get a shorter growing season, what's going to happen is every year you're going to have to start over. And that slows speciation. Generates more evapotranspiration. What's evapotranspiration? Besides just being a really big word. What?
Cooling by evaporation.
Say it again.
Cooling by evaporation.
What?
Oh, it's
Evaporation through trees. Evapotranspiration. What's happening is the trees, plants, are absorbing water through their roots. They need it for photosynthesis. They take it up the xylem, out to the leaves where photosynthesis occurs, but not all the water stays there. It exits the stomata when the guard cells are open. Remember all these terms? Nice little review there for 5 seconds. You're welcome. And what happens is it escapes into the atmosphere. So it's a plant's way of returning some of the water to the atmosphere. It generates more evapotranspiration, and the equatorial areas tend to be older. The polar communities, pretty much just the opposite. Shorter growing seasons, speciation start over due to repeated disturbances like glaciation. If you have a harsh winter, you're going to have to start over. If you have glaciers come down, wiping everything out, really, really cold environments, and then they recede, again, you're starting over. Virtually no evapotranspiration. Why is that?
No trees.
No trees. You don't have many plants. And these communities tend to be newer because they are refreshed almost every year. I mean, when you think of a tropical rainforest, what pops to mind are all the different kinds of plants and animals. And then you think of a polar community, you don't think of too many plants. You think of a few animals like polar bears and penguins, just at opposite poles, remember? Maybe some seals or sea lions, the Arctic hare, fox, wolf, whatever. Ptarmigans, which is a bird. Snowy geese. All these things, but not a lot. So there you have differences between equatorial and polar communities. Area effects, biogeography. When Darwin was asked questions about biogeography, he always referred to Wallace. Wallace knew better. Darwin left, traveled around the world for about 6 years, got back, never left England again. Wallace spent so much more time in so many different places. Area effects. Larger geographic areas of community support greater numbers of species. Well, that's kind of like a state. You have a bigger area, you can support more different kinds of animals, plants. Larger geographic areas of communities produce greater diversity in macro and micro habitats, what we talked about. Even in smaller habitats, you're going to find greater biodiversity. And if you find it in smaller ones, you're going to find it in bigger ones. So just plain and simple reasoning. The larger the area, the greater number of species. Whether we're talking about macro or micro habitats. The larger the area, the greater the number of species. This is where we're going to stop. I'm going to read your exams and hand those back. Write that down. This is where we'll pick up on how area affects species distribution, species survival, immigration, extinctions, all kinds of things. Larger geographic areas of community support a greater number of species. That's kind of like a statement. If you have a bigger area, you can support more species. Larger geographic areas of a community produce greater diversity in macro and micro habitats. If you have this big space, chances are it's not all going to be geographically consistent. It's going to break down into smaller areas, macro, micro habitats. And in those areas, you're going to find greater diversity. So if the landscape's diverse, the species are going to be diverse. Island habitat. Any area surrounded by a different habitat not suitable for the island species. If you're terrestrial and you're surrounded by water, you're stuck on the island. Okay? And especially if it's an island with not much access to the mainland, at least not close. Couple of things here. We've got Australia. In the middle of Australia, we've got the desert region. Most organisms live on the coastal region, people included, of Australia. That's where you find a lot of animals, unless they are adapted to living in the Arctic. So island habitat. In fact, from here on out, the island equilibrium model, we're going to be talking about Australia. It just lends itself pretty well to this. Put the examples up and use it. So island habitat, any area surrounded by a different habitat not suitable for the island species. If you're terrestrial, the aquatic area, the ocean around you, you're not going to be able to get off the island. Number of species to inhabit an island is determined by two things: rate at which species immigrate to an island, Now we've had immigrate and emigrate. They're pronounced the same, but just to distinguish it between the two different terms. This is organisms immigrating or coming to the island. Now you might be thinking it's an island. How are they going to get there? Cruise ship or something like that? Cargo ship? Well, maybe sometimes. Sometimes people bring them. Sometimes a disaster like the Galapagos finches of Darwin got blown off by a natural phenomenon. Rate at which native species go extinct. So you get a species like the dingo immigrating to Australia. And then you've got the Tasmanian wolf, the thylacine, already there. Now, two similar organisms, occupying similar habitats, similar behaviors, hunting similar prey. This is a marsupial, this is a eutherian, okay, placental, a little bit better adapted. Plus, the Tasmanian wolf had the pressures that once people got there, much like the gray wolf in this country, they got hunted literally to extinction. That's why the picture is kind of fuzzy. Not a lot of recent pictures of Tasmanian wolves. So rate at which species immigrate to an island, how fast they get to the island, and rate at which native species go extinct. So you have some coming in and some leaving, not by their own choice and not by a fun way. The dingo was introduced to Australia about 4,000 years ago due to overlapping habitats. The dingo may have directly contributed to the extinction of the Tasmanian wolf. Therefore, people might have just been the last straw that broke that camel's back, chased it into extinction, which had established itself in Australia over 23 million years ago. So here's a situation where something was uniquely suited to a particular habitat with specific habits that it probably couldn't change quickly enough for the introduction of a competition of the dingo. And so the dingo just outcompeted. And you can see where the dingo has been common, actually does live throughout the outback, generally common on the edges here. Some here in the white areas, it's never been seen before, so you don't see it all over Australia, but through a major portion of it. Factors affecting immigration and extinction, number of species already present. How many canid species are on the island? Well, in this case, there was the thylacine, the Tasmanian wolf, and then the dingo, so direct competition for each other. What if there were a number of things? Trying to introduce like the dingo to the U.S., it may not do as well because not only would it have the wolf to compete with, but also the coyote. Distance of island from the mainland. Like I said, here's Australia right here, out in the middle of the Pacific and Indian Oceans. And you have some other islands here, which are a pretty good distance away from most of the mainland. You have to go this way, or around this way over here. You know the Earth is round, right? Just check. And the size of the island. Well, Australia is a pretty good sized island. If it was small, then obviously the immigration rates would impact the island more, and the extinction rates would probably be higher and faster. Because it's a decent sized island, it's the biggest island, I think, in the world. The only island country continent. About the same landmass as the U.S. So that's pretty significant size. So it's going to be able to support a lot of stuff before it really starts to feel the impact. But once it does, because it's an island, everything's pretty much stuck. They've got nowhere to go. Number of species on an island will reach an equilibrium between the rate of immigration and the rate of extinction. Eventually, the dingo outcompeted the Tasmanian wolf. Like I said, people also had issues with the Tasmanian wolf, so it was getting pressure from a lot of different sides. And eventually it lost out, and the dingo succeeded. So the balance here was the Tasmanian wolf is gone, the dingo is still here. Still there.
Do you think the Tasmanian wolf got outbeat by the dingo because of the size? Was it much bigger? Is it relatively the same? Or?
I think size was relative. They were about the same. The dingo might have been a little bit bigger. The the Tasmanian wolf was a marsupial, so the reproduction rates would have been a little bit lower. I mean, you can only have so many offspring at a time. The dingo could have had more offspring. So that could have created a situation where they outcompeted reproductively. And then, for some reason, the Tasmanian wolf was out-hunted more than the dingo by people. So maybe it was like the wolf and the coyote. We don't like coyotes, but we tend to coexist with them more than we would wolves. I mean, look at mountain lions, on par with the wolf. We have a mountain lion in our community, they go out and they hunt and kill it. We have coyotes in the community, we just try and chase them out. So, the human factor had a lot to do with that. Okay, changing gears a little bit. Zoonoses. A zoonotic disease. Again, you've got ZO there in the front. It has to do with animals. Any infectious disease capable of being transmitted by vertebrate animals, wild or domestic, to humans. So it's vertebrate animals. In the past, people get this confused. They give me examples of invertebrates, and that doesn't count. It involves bacteria, parasite, and viruses. And yes, I know bacteria, parasites, and viruses are usually not vertebrates. I mean, the bacteria is prokaryotes, most parasites are protists, and then of course viruses, but it's when they infect vertebrate animals, and then the vertebrate animal spreads that disease to humans. Over 200 known diseases, they've been known for centuries. Viruses were first discovered by Louis Pasteur, and he did it studying rabies. And he couldn't figure out how a rabid dog could pass rabies to a healthy dog. So what he did was he took a rabid dog, took the brain tissue out, and injected it into a healthy dog, and the healthy dog developed rabies. Now, still wasn't clear what viruses were, but knew there was some kind of infectious agent that was transmissible, something that could cause a disease that could be carried from one organism to the other. And thus, this whole idea of viruses began. And that was looking at the late 1800s. And of course, one of the more recent zoonotic diseases that made the news was the swine flu. So any infectious disease capable of being transmitted by vertebrate animals, either wild or domestic, to humans. Yes.
Did someone in Canada contract Ebola?
I don't know. I have not heard that. The thing I keep hearing about now is MERS, Middle Eastern Respiratory Syndrome. But evidently, one or two people were flying back on a plane from the Middle East, and now they're telling everybody on the plane to check. Two people that have it are expected to recover, but it is a considerably lethal disease. Full blown, it could kill people. But I've not heard about Ebola in Canada. I believe that's a name.
Well, some of that
Came from Africa? Yeah, that could have been. That's a nasty disease. Examples of zoonotic diseases in your outlines. Anybody have the outlines for today? Did I not give you all these already?
Yes.
Okay, so I'm not going to spend a lot of time letting you write this down. It's on Blackboard. Avian influenza, birds. Bovine spongiform encephalopathy in cows. What's that otherwise known as? Mad cow disease, or sometimes just BSE. Ebola in primates, like you mentioned, that is one here. Hantavirus in rodents, this is something we get out here in the West. The plague was caused by rats. It wasn't really the rats, it was bacteria living in the ticks that affected the rats. The rats were killed. They assumed room temperature. The ticks needed warm-blooded animals, so they jumped from the rats to the people, and then it spread. But it started with a bacterium, but there was a vertebrate animal factor, that being the rats. Rabies, raccoons, dogs. I like that picture. That looks like a seriously rabid raccoon. Scary. Swine influenza with the swine flu pigs, toxoplasmosis, we've already talked about cats.
Oh.
Factors, I know. And that picture was really circulating about the time of the swine flu. I'm thinking, really? I mean, it's not like chicken pox. Go down the street and play with the little kids so you catch chicken pox. Go look at pig snout, say you get swine flu. It doesn't work that way. Factors lead to the emergence of zoonotic diseases, changes in the environment. What do we mean by that? What might allow diseases to spread?
It gets really cold, and
and people clump together inside.
There could be that, really, really cold winters, because that's when we get sick more often with things like the cold, the flu. They even call it the cold and flu season. It's not that it's so much the weather, it's just we spend more time indoors, more time with each other, exposing each other to more things. What else though?
Well, heat makes it grow, doesn't it?
Okay, now how does heat apply to the environment?
Global warming.
Global warming or climate change. And what's happened is maybe the winters don't get quite as cold, maybe the growing seasons, the warmth extends away from the equator, farther north and south, spreading those diseases that were mostly tropical or spending time in subtropical areas. Now they're spreading farther away so they can infect more people. Changes in pathogens, they mutate, they adapt. So even if we develop a vaccine against something, that doesn't mean that that vaccine is going to work in the future against something similar. And social and cultural factors. Don't let your kids look at pigs. It's never good. We spend more time around each other. We travel more. We're more of a global planet now. I mean, it was amazing that Spanish flu infected as many people as it did, killed as many people as it did. 35 to 40 million back in 1918 when we were a relatively closed off society, but it was World War I. Started with the U.S. It infected troops here, went to Europe, took it over there, and then everybody they were exposed to, all the people at the end of the war, took it home with them. It's called the Spanish flu because per capita Spain got hit the hardest, losing the most people. Then they came back, the soldiers, the U.S. soldiers, back to the U.S. and brought it back here, and then we had a secondary infection. But if it wasn't for the war, it wouldn't have spread like that. Today we don't need a war. We travel. We get on a plane. We get on a ship. We go places. And we encounter more people from other places. So it's really easy for us to become global. Like